All right, so this is an example on how to do graphing radical functions. I'll just work out the first one and talk about how you do it. So first off, you've got the equation and then they're asking for the intervals of increase and decrease. Let's do these later. Let's first sketch the graph. Now, I think it's helpful if you know roughly what the graph looks like. And for that, you should just go to Desmos, that free online graphing calculator, and plug this equation in and just have a look. You can see what the graph looks like. I want you to know roughly what these shapes look like. I'll say off the top of my head, I know that this graph will look something like this. It's a kind of a curve. It starts one place and goes off like that. This one will look like that too. These two will have a similar curve, but since there's a negative in the front, it'll kind of flip them over the x-axis or flip them in the x-axis and make them kind of curve down like this. But yeah, knowing roughly the shape is important. Then we're going to make a table here and use this table to kind of guide where the points are and then draw a curve off there. Now, you could plug in any numbers you want. If you check on Schoology, the little lesson at the bottom, you have to kind of scroll past all the videos at the bottom. They actually have a few tables, and they start with numbers like -3, -2, -1, 0, 1, 2, 3, like kind of the standard table. What you tend to find for a lot of rational functions is a negative inside a square root gets you an error. I mean, I could prove this with a calculator, but this is just one of the rules of math. You have the square root of any negative number, say -2 or whatever, you get an error. It's technically an imaginary number. But yeah, you're not going to have the function show up for any negative numbers. So I like to just start my table at the first number that it will actually exist at, which will be 0. So when x is 0, you plug in 0 here, what will you get? And again, if you need to use a calculator, feel free, but this is be 2 square root of 0 plus 4. That's just going to be 0 essentially plus 4, because square root of 0 is 0. 0 times 2 is 0. Add that to 4, you get 4. So there's our first point, actually. That'll actually be this point right here. And I know that because I know that anything to the left, so to speak, any negatives wouldn't even be showing up. They'd be errors, and so won't be part of the graph. You could plug in a few other numbers. I'm going to do things like 1. Let's show what happens there. So that'd be the square root of 1 times 2 plus 4, so that's 6. Now I could do something like 2 next, and you can do that if you want as well. As you'll see, what will happen here is the square root of 2 is a radical number. My calculator shows it in what's called simplified radical form. If you convert that to a decimal, it's basically a big decimal. So I'm going to intentionally just pick numbers which are perfect squares. So things like 4 or 9, or I know it's a little scrunched here, 16, because then when you plug them in, you'll get more exact numbers. So the square root of 4 is 2, 2 times 2 is 4, plus another 4, you'll get an 8. You do 9, square root of 9 is 3, 3 times 2 is 6, 6 plus 4 is 10. I'm just speeding this up because I can do them all in the calculator. The last one, the square root of 16 is 4, 4 times 2 would be 8, 8 plus 4 would be 12. I'm actually going to stop there. If you want to fully fill these out, it's okay, because I just need a few to be able to plot my points and draw a graph. So let's plot these points. So the first one's at 0, 4, 0 over, 4 up, it's about right there. Kind of the most important point is it's kind of the starting point. Next one is 1 over 6 up, so it puts you 1 right there. Next one is 4 over 8 up, so 4 over A. It's 4 over 8 up, which is right there. And then the next one is 9 over 10 up, which would be about here, and then 10 up puts you about there. So you got these points, and again, if you know roughly what the curve should look like, instead of trying to draw a straight line through these, this is now some kind of leveling off curve. It actually doesn't fully level off, but it curves up more steeply at the beginning than it does later on. If you want to think about it as being a sideways parabola, like that big U parabola shape, but just on its side, but only half of it, that's actually an accurate way to think about it, but that might be confusing. So I'll just say it's a little curve that kind of just goes whoosh, like that. Okay. With that drawn, now I can more easily get all of these things. So real quick, interval of increase. If I was a little bug walking on this graph, hold on a second. I guess I'm a four-legged bug. I don't know, a dog. But if I was a little thing walking along this graph, as it goes left to right, and that's important. We read left to right, so we travel along the graph left to right. Would this bug be going up or down as he traveled along the graph? And he would clearly be going up. It'd be going up the whole way. This graph never curves down. It keeps going up forever, even though it's slower and at a slower and slower rate. So this graph is always increasing, starting at where it starts. We measure interval of increase along where it starts on the x-axis, by the way. So like, think of the x-axis as like time. So at time, and this would be 0, it starts increasing, and it continues to increase all the way to what we say is infinity. So we represent the interval of increase from 0 to infinity, like that. Where is it decreasing? Well, this graph never decreases. So I would just say none. The domain is going to be very similar to the interval of increase. And in fact, for all these, it's going to be whatever the interval of increase or decrease is, it's going to match the domain. Because this function only exists from, again, this 0, and then it goes forever to the right to infinity. So the domain is also 0 to infinity. The little bracket means it includes at the 0, and you always put a parenthesis around infinity. These are kind of minor things if you don't get them. It's more of a first semester kind of lesson. Range is how low versus how high the graph goes. So this is where you now look at the y values. The lowest this function ever was the 4, and then it just keeps going up from there. So the range is 4 to infinity. So it just goes up to infinity. So we'll use the same kind of symbology. And lastly, your x and y intercepts. So the x-intercept is kind of funny. That's got to be where you cross this x-axis. And sometimes the graph is shifted up like this, it never touches it. So don't even worry about it. It doesn't touch the x-axis at all. There's no x-intercept. But the y-intercept, well, it does exist. It's right there at the 4. And you can label it as 0, 4, or just 4. But anyway, that's the first example. The rest look very similar. I will just point out that this one will also look something like this. But it will be like, its starting point will be to the right one in 3 up. And then these two will be curving down because of that negative. If you use Desmos, you'll see it better.